Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, there is another example related to the implementation of goodness of fit test. So here we have 3 coins that are tossed 72 times, and the number of heads is as shown in the table. So here 0 head, 1 head, 2 head, 3 heads. So imagine if you have three coins, and if you toss them together, you can get 0 head, which means all the coins here give you all tails, or you can get maximum of 3 heads because all the coins that you toss give you heads. Alright, and using the 5% significant level, test the null hypothesis that the coins are balanced and randomly tossed. And here are the frequency that you observe, and you can see that the total number of this is going to be equal to 72 times. Right, and so we are going to start off with writing down the alternative and the null hypothesis. Right, as you can see here, this is the idea or some sort of a pattern. The pattern here is coins are balanced and randomly tossed, and that is what we're going to consider as the null hypothesis. We can say that coins are balanced and randomly tossed. Therefore, the alternative hypothesis is going to be coins aren't balanced or are not balanced and aren't randomly tossed. Okay. Now, in order to compute the statistical test, so here is the computation. We need to compute what is the chi-square value, the test statistic, which is given by this formula: observed minus expected value squaring over the expected value. And we need some sort of simple calculation. Therefore, I think what we need to do is we can construct a different table, a slightly different table that looks like this. So here is the categories involved. So we have the first category, second, third, and fourth. So this is the number of heads, H, and this is the observations. So here is the observed frequencies, 3, 10, 17, 42. And first of all, we are going to assume that if the null hypothesis is true, that the coins are balanced and randomly tossed, what would be the probability of observing 0 head, 1 head, 2 head, and 3 heads? Now, here is the problem where the majority of students will get stuck at this point, because they will give the answer as 1 over 4. They will think that the probability of observing this will be 1 over 4, 1 over 4, 1 over 4, 1 over 4, and this is wrong. Okay, so this is wrong. But this is the common mistake that students always make. Now, the real answer to this one is going to be 1 over 8, 3 over 8, 3 over 8, and 1 over 8. I'm sure you notice that probability here is different for each category. Now, in order to explain to you what's going on here, we have to go to the very basic idea of probability, and tossing 3 coins is a classical example, which I'm going to illustrate to you right now. So you can imagine if you have 3 coins that you randomly toss, and if it is balanced, therefore at this point here is tossing the first coin, and you will get head or tail, and if you go on, you will also get head and tail of the this is the tree diagram, which at this level here represents the outcome that you will see on the first coin, and this one here the outcome that you will see on the second coin. And because you have 3 coins, so we go on to create another level. So here we can get head or tail, here we get head or tail, and this one here we get head or tail. Right, so now if you look at the probability, if the coin is balanced, that means the coin is fair, the coin is balanced, the probability of getting head or tail is going to be equal. This is going to be 1/2, this is also going to be 1/2. So this is for the first coin. Similarly, if the second coin here is fair, the probability is going to be the same. 1/2 and 1/2. Similarly, if the third coin is fair, the probability is going to be 1/2, and all of this is going to be 1/2, yeah? Okay. Now, if you see the root that we have, we now have one root, one path. This is the second path. This is the third path. This is the fourth path. This is the fifth, the sixth, the seventh, and the eighth path. So you have 8 different paths here, and for each different path here, you can see that for this one here, you will have 3 heads. Yeah, 3 heads. For this one here, you will have 2 heads and 1 tail, right? And for this one here, you will have 2 heads. Why am I focusing on heads? Because this question is related to the number of heads. All right, so here is 1 head. For this one here is 2 heads. This one is 1 head. This is 1 head, and the last one is 0 head. I'm sorry, I hope you can see it clearly. And the probability of getting 3 head for this one is going to be just 1/2 times 1/2 times 1/2 for this root. So you will have the probability is 1/8. Now similarly, if you want to get 2 heads, the probability is 1/2, 1/2, and 1/2. So this root here is for this one. So here we have also 1/8. And you can see that for each root here, the probability is the same, because at each level here we have the same 1/2 value. So we can see that probability of this is going to be 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, and 1/8. Now, if you look at the probability of getting 3 heads just appear on this part. So the probability is 1/8. So this is the probability. Sorry, this is the probability related to getting 3 heads. The probability is 1/8. If you look at the probability of getting 2 heads, the probability of getting 2 heads will be this part and this part. This is also getting 2 heads, and this part. So you need to add up the probability here. So the probability will be 3/8. So this one is 3/8, the probability of getting 2 heads. Now, how about the probability of getting 1 head? The probability of getting 1 head is this one, and this one, and this one. So it will be 3/8. And finally, you can see that the probability of getting 0 head is just this one. So 0 head is just 1/8. So therefore, the probability here is given as 1/8. So basically, this is how you obtain probabilities for each categories when the null hypothesis is true. So when the coins are balanced, or the coins are fair and randomly tossed. So this is the probabilities that we can come up with. Alright, I'm just going to erase this part here because it looks a little bit messy, but I hope you get the idea. So I'm just going to erase this. Right. So now, based on the probability that we get, so this is the probability, then we can go on and find what is the expected value by multiplying n with each probability for each category here. So this is what we will get. So 72 is divided by the respective probability. So you get 9, 27, 27, and 9. So these are the expected values. Right, next we are going to compare the observed values with the expected values here. So you are comparing, you want to see how different your result is compared to what you would expect to see. and you will get this value. And since you're going to square it, the answer is going to be all positive values. And we're going to use these answers here in order to obtain the test statistic. Right, therefore, the test statistic is going to be the summation of 36 over this one, 36 over 9. So you take this value divided with the expected value. Next, plus 289 over 27. Next, you will plus 100 over 27. And finally 1089 over 9. And the answer that you will get is going to be 139.407. Okay, so if you apply the traditional approach, traditional approach here will be related to finding the critical value. And this is the right-tailed test, therefore the critical region is on the right side of the distribution, where the area is going to be equal to 0.05. So the area is 0.05, and you need to find what is the value here on the horizontal axis, such that the area from this point to the right is 0.05. So we need to find what is the critical value. And let us refer to the chi-square distribution table. Oh, hang on. What we can do is, before we can find what's the critical value, you need to know what's the degree of freedom. And the degree of freedom is equal to the number of categories minus 1. The number of categories here is 4. 4 minus 1 is equal to 3. So the degrees of freedom is equal to 3. Right, now let's move on to find the critical value. So here is the chi-square distribution table. The area is 0.05, degrees of freedom is 3, and so we can refer to this point here. So this is the critical value, which is equal to 7.815. Oops, sorry. Okay, so the critical value is equal to 7.815. So this is critical value. Now, in order to decide whether the null hypothesis can be rejected or not, we need to compare the result here with respect to the critical value obtained on this step. So you can see clearly that this value 139.407 is going to be way forward compared to this value here, 7.815. So we can clearly see that the test statistic here falls into the critical region, and therefore we say that the test statistic 139.407 falls into the critical region. Therefore, H null is able to be rejected. And next, we're going to write down the conclusion, which is there is enough evidence to say that coins are not balanced and are not randomly tossed. Okay, coins are not balanced and are not randomly tossed. Alright, and here is something for you to work on yourself. You may want to demonstrate how the previous example can be solved using the p-value approach, and this one I leave it to you guys to do it on your own. Alright, thank you very much for watching.